All right, so we weren't completely done with 6A last time, so we're going to wrap that up tonight as well as 6B. So here we're still looking at series where we're trying to perform different operations on them. It turns out that we can actually differentiate and integrate a power series just like any other function. So here's our general expression for a power series. We have the sum from n equals 0 to infinity. We have a constant in front of each term, c sub n, and then we have x minus a to the n power. And so that can be written out as c0, which is of course a constant, plus c1 times x minus a, plus c2 times x minus a squared, plus dot, 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 all the way up to infinity. Now we're assuming for what's about to follow that it converges in some interval. It doesn't have to be on the entire real number line. As long as there's an interval over which it converges, then what we can do is express this as a function, and that will apply to all x minus a, absolute value x minus a within that range of convergence. And then if that's the case, then f of x is differentiable. And what we're going to do is actually just simply apply the power rule to each term one at a time. And here's what we're going to wind up with. Okay, so we have, starting with the original expression, we use the power rule. So we end up with n times the constant Cn times x minus 1 to the n minus 1 power. All right, so this is no different than any other time we've ever used the power rule on, let's say, something like this. Let's say, actually, just n k x to the n minus 1. So that's exactly what we're seeing here. This n, the exponent comes down and becomes the coefficient. Then we still have Cn, x minus 8, and now the exponent has 1 subtracted from it, so it becomes n minus 1. So the result is C1 plus 2C2 times x minus a plus 3C3 times x minus 8 squared plus all the way on to infinity. Now, of course, we can do the same thing with integration. And we apply the same rules. We'll apply the power rule, as a matter of fact, to each term, which you recall the integral is the integral of x to the n dx becomes x to the n plus 1 over n plus 1. Now here, we're not going to add that additional c. It's already in the series. So when you integrate this one, this is the general expression for it. Of course, you notice that it's just exactly what we did here. And so you end up with the constant. This constant can be moved up front. And then the rest of these are the constants that we already had in our series. C0, x minus a, plus C1 times x minus a squared over 2, et cetera, within the interval of convergence, which could be the entire real number line, by the way. All right, now let's look at some specific cases. So the power series representation of 1 over 1 minus x, assuming that the absolute value of x is strictly less than 1, is 1 plus x squared plus et cetera, all the way up to infinity. And so we end up with f of x is 1 over 1 minus x, could be rewritten as the infinite series from n equals 0 to infinity of x to the n power. And again, assuming that this is true right here. If not, it diverges. So what if we have something like this? Since f of x is 1 over x, 1 minus x, or 1 minus x to the minus 1, then it stands to reason that f prime of x is minus x. But by the chain rule, we also need a negative 1 here. So we end up with, sorry, this is 2. X, 1 minus x, to the minus 2 power, which is of course just 1 over 1 minus x squared. So over the interval -1, 1, we can differentiate this, or we can rewrite it as the derivative of 1 over 1 minus x. This was the original function. And so it's the derivative of x to the n power, the series. So it's equivalent to the derivative of 1 plus x squared plus x cubed plus dot, dot, dot. And then when we actually apply the power rule, we end up with 0 plus 1 plus 2x, et cetera, et cetera. So what this means then is that this function can be expressed as this infinite series. And so how do we, that took a lot of cleverness to recognize that g of x is simply the derivative of 1 over 1 minus x, which we'd already looked at earlier. And so it stands to reason that the derivative would have a series representation which is related to it. So if f of x, once again, is 1 over 1 minus x, it can also be written as n equals 0 to infinity of x to the n so its derivative is just this. Okay, now how about this one? Find a power series representation for f by integrating the power series for f prime and then find the interval of convergence. So f of x is the log of 1 plus x. And of course, that implies that the derivative is 1 over 1 plus x. Just, of course, as you recall, if f of x is the log of g of x, then f prime of x is g prime of x over g of x. And that is what we have here. G of x would have been the 1 plus x. And the g prime of x would simply be 1. So g prime of x over g of x would just be 1 over 1 plus x. Now, sometimes it might pay to rewrite these expressions. Here we have 1 over 1 minus minus x. Why are we doing this? Because this will make it look more like a series that we've seen before. This one in particular, you might recall that 1 plus x squared plus all the way up to infinity, which can be written like this, converges to 1 over 1 minus x. And again, only if the absolute value of x is strictly less than 1. Well, if that's the case, what happens to this one? Let's find out. So that means that 1 over 1 plus x converges to not n equals 0 to infinity of x to the n, but minus x to the n. Okay. Now, in order to rewrite this expression as a power series, if we integrate, and remember what we had was this. So that means you're going to get minus x to the 0 plus minus x to the 1 plus minus x squared plus minus x cubed. And that simplifies to minus 1. Oh, sorry, this is minus. 1 minus x plus x squared, alternating to signs, and we'll end up, and here's of course the integration, the constant of integration. And so this is our final result. Now, if you really need it, you can actually calculate c out of this, because we know that f prime of x is 1 over 1 plus x, which we just set through equal to this integral. And then we can set it equal to this expression. And so what this implies is that, based on the result we had before, if you set these equal to each other, this is our final result right here. All right, now this next section is two of the most important results in this area that are used constantly in applied areas to come up with approximations to very complicated functions. And they're referred to as Taylor series and Maclaurin series. So all right, we'll see as we go along, but these are two of the more important techniques we'll be learning in this chapter. And they're used for finding power series representations for functions. So we start here with this expression, which is clearly a power series, except if you notice here, of course, x has a subtracted from it. It's a constant, but this is still a power series. The first one we saw was this one. And so all we've done here is subtract the a. All right, and so this is what it actually looks like. C0, which is a constant, plus C1, x minus a, plus C2, x minus a squared, et cetera, et cetera. Now, if we evaluate this thing at a, it should take on the value f of a. Okay, this is some function or other. And so evaluating it f of x equals a should result in f of a. So what we're going to do here is actually replace all those x's with a's. And so you notice how all the terms drop out except for this one, the initial constant. Okay, so what that indicates is that when x equals a, the constant here, C0, has to equal f of a, whatever that is. And the derivative of the power series will give us f prime of a when x equals a. So we differentiate this as we saw earlier. And once again, when x equals a, all of these drop out. So what that implies is that f prime of a has to equal C1. So f of a is C0, f prime of a is C1. Now, of course, we're going to continue to do this by taking higher order derivatives. And this is the result which we will be using. If you notice what's happening here is that we have the sum of f taken to the nth derivative. This actually represents the 10th derivative. Sorry, nth derivative, I should say, of x evaluated when x equals a. And this is what it looks like. Now, as far as applied work is concerned, it's these first few terms that we really want to use to approximate a much more complicated function. Okay, and often in practice, we don't need to go past the first 2 or 3 terms to get a good result. You'll see with some graphs that we have here that after 2 or 3 terms, that's often sufficient to come up with a very good approximation to a function. Now, based on this general result, when x is centered at a, or x equals a, this is called a Taylor series. When x equals 0, We call this a Maclaurin series. Okay. Now, we're going to create what are called Taylor polynomials. They're actually partial sums, like we saw earlier. And so we're going to write them in a very specific way based on what we just saw. This term, this expression here. P0 means just this term. P1 is these first two terms put together. Okay, notice f of a plus f prime of a x minus a. P of 2, second Taylor polynomial, would therefore be f of a plus f prime of a x minus a plus that third term there, f double prime of a over 2 factorial times x minus a squared. Okay, and then, we can take it as far as we need to. There's we can have number 3 as well. But like I said, in practice, it's often not necessary to go out quite that far. But this is what it would look like. So these are known as special names. P0x is called the 0th polynomial, believe it or not. This is the first, just simply P1x, P2x, and finally P3x. Taylor polynomials of f evaluated at x equals a. Okay. If x equals a, then they reduce to Maclaurin polynomials. So here's the nth Taylor series polynomial. That's the general expression. And of course, you notice how we have to assume that all these derivatives exist in the first place. Otherwise, we can't do this, obviously. And so what we're going to do is a few simple examples which show exactly how this works and how closely they approximate the actual function. So we'll start with a simple case, log of x. Okay, so you know that log of x looks something like this. We're going to evaluate it at x equals 1. So here's 1. And when x equals 1, y equals 0. So what are we trying to do here? We're trying to come up with a polynomial that gets really close at that point. Okay, like this blue line could be a Taylor polynomial, and it is meant to get very close to the function, at least at this one point. I mean, it might get close at other points, but that's the one that we're interested in. That blue line is what we're trying to estimate with our Taylor polynomials. So basically what we have to do is try them and see how close they actually get to see, is P0 sufficient? Is P1 enough? And then we'll see where it goes from there. Now, in order to do this, in order to create this Taylor polynomial, if you notice, we need a bunch of derivatives, and we have to evaluate the derivatives at a particular value that's given to us. Okay, so here, since the function is log of x, we know that the derivative of log of x is just 1 over x. Now, we're evaluating this when x equals 1. Okay, so we also need to evaluate the original function when x equals 0, and you can see that's just 0. F prime of 1 is 1. Okay, and then we're also going to use 2 and 3. So we need the second derivative, and we need the second derivative evaluated where x equals 1. And then finally, we need the third derivative and its value when x equals 1. All right, so here's what we're going to do. We're going to make some substitutions. The 0th Taylor polynomial, as it's called, simply equals f of a, which in this case is 1. So remember, the function is log of x. So we end up with f of 1, log of 1 of 0. P of 1 is f of a plus f prime of a x minus a. Remember, f prime of a is 1 over x. F of 1 is 0. F prime of 1 is therefore 1. So what do we have here? F of 1 plus f prime of 1, x minus 1. So when you make those substitutions, you'll have 0 plus 1 times x minus 1, or just x minus 1. Okay. So the 0th Taylor polynomial is 0. That's obviously not going to do us any good. The first Taylor polynomial is a linear function, x minus 1, which will not do a horrible job of approximating this function, but it's not the best. What about the next two Taylor polynomials? All right, so we need, as you can see, f of 1 plus f prime of 1, x minus 1, plus f double prime of 1 over 2 factorial times x minus 1 factorial. And we just got through showing that f of 1 is 0, f prime of 1 is 1. What about f prime double prime of 1? Let's go back here. The second derivative is minus 1 over x squared. F double prime of 1 is therefore just simply minus 1. Okay, so, but we don't want to forget about this little detail. So this is, it's true that this is minus 1, but we're dividing that by 2 factorial, which is just 2. So this is actually equal to minus a half here. Okay, so when you do all the calculations, you end up with x minus 1 minus a half times x minus 1 squared, which is clearly a quadratic function. Okay, and then taking this one step further, we're going to do the third order Taylor polynomial, and we end up with a cubic function. So now it's hard to visualize, but just by looking at this, what we've done, the book, luckily for us, has a nice little graph here where it shows all of them, including the correct function. And this is what they're telling us. We have the original function here. Sometimes it's hard to tell because there's only a couple of colors in here. The first polynomial, it's a straight line. This blue straight line here is P1. P2 is this one down here. It's a quadratic function. Now, remember too, we're looking to approximate the function when x equals 1. And then 3 is way up here, this red curve. This is a cubic function. What you'll notice is that all of them seem to look pretty close where x equals 1. So what really separates the 3 or 4 of them is that at least the higher order Taylor polynomials will continue to give us a pretty good approximation, even if we get further and further away from the point of interest, which in this case is x equals 1. So which one you use depends on how accurate you really need to be. So, but you can see that we could keep going. If you keep choosing higher order polynomials, the functions that you're creating are going to get very close to the original function. So once again, what we're really interested in is how closely do these approximate the original function and how much accuracy do we really need? That's what's going to determine how what order Taylor polynomial we use to approximate our function. Let me just throw up there a quick example from finance. In finance, the relationship between bond prices and yields looks something like this. So we may want to have some idea of what happens if we start here, this price and yield. What happens if I move, let's say, down here to 6? What would be the new price of this bond? Well, we don't really know for sure, but if we have a Taylor series polynomial, let's say P2, which is going to be a cubic function, it'll probably give us a very good idea of where the new bond price is going to be once the yield changes. So think of this as P2 of X, the second Taylor series polynomial, and the original function is here. Now, when this is really helpful is in a case like this. This relationship is a result of doing a large number of calculations. The function itself is quite complicated, and recalculating it might be quite a burden. So instead, it might be quicker and easier to simply use a Taylor series approximation to find the new price of the bond when the yield shifts over to 6%. All right, well, anyway, now Maclaurin polynomials, they're similar. What's different is where they're centered. Okay, so we're going to try to come up with an approximation for the function f of x equals e to the x. And so, of course, we know what that looks like. With this one, we're going to use the first 3 or 4. Let's see, how far did we get? Yeah, we're using the first 3, actually the first 4 from 0 to 3 Taylor polynomials, which means we need the first 3 derivatives, and we have to evaluate everything here because it's a Taylor series. It's a Maclaurin series. That means the center is assumed to be 0. Okay, so these are the calculations we really need. First, and of course, this is a particularly simple case because we know that no matter how many times you differentiate this function, we're just going to keep getting e to the x. So when we evaluate at that where x equals 0, we'll just end up with 1s every time. So when you plug these in, now if you notice what's missing, these 0s are replacing the a's in the Taylor series. Okay, it's understood that there's automatically 0s because it is a Maclaurin series. With the Taylor series, it could be any A. So ultimately, what we're going to end up with is this. Okay, 1 plus x squared over 2 plus x cubed over 3 is approximately equal to e to the x. It's only approximately because it's we don't have all of the terms, right? To make it exact, we need the entire series. And then we can rewrite it in a very interesting way. If you keep going, you'll see that in general, here's what you have. You've got the infinite series, x to the k power over k factorial. This equals e to the x. Now, here's another graph which shows us how close the Maclaurin polynomials are coming to the original function. And again, remember that we're trying to get as close as we can at 0. And they're all very close at 0, but as you move further away from 0, this one deviates quite a bit because it's a linear function. This is a quadratic function. And this cubic function actually looks pretty close for a fairly long range of x's, but eventually even it will not be adequate to correctly explain the behavior of f of x equals e to the x. Now, here's one. Now, this is what I was alluding to earlier. Often in practice, we only really need a linear and a quadratic approximation to do a good job of approximating a function. So let's just say we're looking at the cube root of x. So we're going to create some Taylor polynomials at x equals 8, which would be here, let's say. And so this is really no different than what we did earlier. It's just that we're going to stop at P2. We just want P0, P1, and P2. And so the function is cube root of x. So the first derivative, as you can see, is 1/3 x to the minus 2/3 power. The second derivative is negative 2/9 x to the minus 5/3. When you evaluate all three of these at 8, you get 2, a 12th, and finally negative 1 over 144. So let's fill these in. Okay, actually, we're only going to use P1 and P2. We're going to use P1. Now, this is the general expression for the first Taylor polynomial. Remember, this one, we have A instead of 0 because it's a Taylor series. The A is 8. And so we know that f of 8 is 2. The first derivative times x minus 8. Remember, this proved to be 1/12. So we just have 2 plus x minus 8 over 12 for P1, the first Taylor polynomial. The second one is this one. It needs f of 8, f prime of 8 times x minus 8. And then we have f double prime of 8 over 2 factorial times x minus 8 squared. So now we'll plug in the constants that we just calculated. And this is what we'll have. And once again, we have a nice little graph here. It shows us how close these polynomials are really getting. And there they are. So you can see they're looking pretty good. I mean, at least considering we're only interested in this area here. You notice as we get further and further away from x, especially P2 is still quite close to the function f of x. So if you assume that we don't move too far away from that 8, this should do a good job approximating this function. Okay, so that's our discussion about Taylor and Maclaurin series. So this is basically the end of chapter 6. And that is the end of the new material. So we'll stop right here. And then going forward, what we're going to do is just simply, we're going to work on our problem sets. And of course, anybody who needs, maybe wants Zoom sessions, we can arrange them. But as far as the new content is done, we're actually finished with that. So the class officially ends on Monday the 31st. So we're like a week ahead of ourselves here. But this way you'll have plenty of time to work on the assignments. And you have all the slides, you have all the videos, and you can always write and send me email questions if you want. You have the book. And so we should be done in time. And then possibly you're going to take this new knowledge and go on to Calc 3. I personally remember finding Calc 3 to be easier than Calc 2. And there's a lot of interesting material in Calc 3, including matrix algebra, which is awfully important because it's called multivariate calculus. You have multiple variables going on at the same time. So something to look forward to. Okay, so, all right, good night.